And for the first one, and this will be equal to square root pi squared E divided by stress critical. Okay, so this will be equal to square root pi squared 200 times 10 to the power 9. Okay, and then over here, the stress critical is 250 times 10 to the power 6. Right? Because LE is equal to L, right? We have L over R will be equal to 200 power 9 times by pi squared divided by 250 power 6, and then square root the whole thing is 88.86. 88.86. So 88.86, the slenderness ratio L over R is 88.86. Now, next we are going to do for one fixed end and one free end. Okay, so now this will become 2L over R, because our LE now becomes what? 2L. Okay, and this will also be equal to 88.86. And then if we were to do the L over R, this will be 88.86 divided by 2 will be equal to 44.43. Okay. And then the next thing, we're going to look at the same thing. Now, over here, this is equal to 0.7 L. Okay, so we're going to put 0.7 L over R is equal to 88.86. Why all of them equal to 88.86? Because if you look at this equation over here, all of them have the what? All of them have the same all of them have the same Young's modulus, all of them have the same what we call our critical load. Okay, the critical load, and pi is a constant. That's why everything is 88.86. The only thing that is different is the equivalent length, right? This is our LE, and for one end pin, one end fixed, so this will be equal to L over R now, will be equal to 88.86 divided by 0.7 is 126.94. And then finally, the last one is equal to 0.5 L divided by R, and also equal to 88.86. So the L over R will be equal to 88.86 divided by 0.5, 17.72, or 177.72. So what does this values actually means? Okay, so I'm going to draw a case. Okay, I'm going to sketch now, where on our x-axis, okay, this is our L over R, and then on our y-axis, this is our critical load. Okay, and then this will be, hopefully it's enough, 20, 40, 60, 80, 100, 120, 140, 160, 180, and 200. Okay, and then over here, I'm going to, our critical load will be 100, 200, 300, 400. Okay, so let's put everything in. So we have 1. Okay, so one of the lines belongs to 44.43. So it's about here. Then we have 88. We have the next one. We have 88 point. Sorry. We have 88.86. So somewhere around here. And then we have 126. So 126 is approximately over here. And 177. So 177 over here. Okay. So we know that this is for free and fixed. This is for pin and pin. This is for, I think the third one is for pin and fixed. And the last one is for fixed and fixed. The higher the L over R ratio, okay, the better resistance to, or the better resistance to buckling. Okay, right? So if we look at this expression regarding the L over R ratio, okay, so for example, you can use the material has a same length, same cross-sectional area, same cross-sectional geometry, dependent on how it is held, okay, the resistance to buckling increases, right? Remember, I mentioned this yesterday, right? The resistance to buckling is to counter the moment, right? To counter the moment. Remember, that's why we have this elastic curve, and we always counteracting the moment. Okay. So now let's look at what will happen when both ends are pinned. Okay. So when both ends are pinned, I'm going to draw. I'm going to use a blue. When both ends are pinned, you will consider the critical load is constant over here. And then once it hit 88.86, so this is our 88.86 line, right? All of a sudden, the critical load after 88.86 will start to what? Decrease. Again, this is a sketch, okay? So if you look at pin, on the left-hand side of the pin, right? The design criteria is stress is equal to P over A. And this is a common formula that we use, right? We have to ensure that at 250, right, I will calculate the stress will be less than, for example, our stress critical over here on the left hand side. Now, once it is greater than 88.86, right, we now have to change our analysis to buckling and analysis. Okay, buckling analysis. So i.e., now your P will be equal to pi squared EI over L squared. On the left-hand side, okay, with this formula over here, right? There is what? There is no consideration of length at all. When doing buckling analysis, right? Why do I say that? Because if it's less than 88.86, the P is equal to stress multiplied by area. Whereas on the right hand side, when we go into buckling analysis, what do we have? We have pi squared EI over L squared. Okay. So what does it mean if we have both end, one end fixed and one and free? Means you have to start your what? Buckling analysis earlier. So I'm going to change color now. If both of them, one end pin and one end is free, you have to start your buckling analysis much earlier. Okay. When you have the next one, if you have the next one, which is pin and fixed, you can prolong longer. You can use P over A. Then after that, after the value of 126.94, then you have to carry out buckling analysis. And the last one, when you have a load or both end are fixed, you can use force divided by area until at this stage at 177.72, you have to now carry out on your what? Buckling analysis. Okay, so it's interesting like how to design structure to resist buckling. It's not just the cross-sectional area. I repeat again, it's not just the cross-sectional area. It is also dependent on what? It's also dependent on how both ends are fixed. Okay, very, very important. Okay, that you get this right. Okay, so what I'm going to do is as I mentioned earlier, I have uploaded the homework. Okay, I'm going to stop the lecture on buckling here, but I want to look in. I want to look into one question on the homework. Okay, I want to look at one question on the homework. So this question over here, okay, that I will do. I'll not be too long. Okay, I promise you that. I know you guys are tired. So am I. Let's look at. I want to look at this question, and I want to show you how to handle the solution menu. Okay, the solution. Let's pick a difficult problem. Give me like 5 to 10 more minutes. Okay. So we are going to use elastic curve to solve a problem like this. Okay. So the first thing that we do is we draw our free body diagram first. Okay. The objective is to calculate direction at point B. And I don't think this is only possible by using elastic curve theory. You cannot solve this just by using static analysis. Okay. So by drawing the free body diagram, this is our point A, and this is our point B. We know that over here, this is our BY, and we have our equivalent load over here, which is equal to omega naught L divided by 2. And we are aware that we have a distance from here to here. This is equal to 2L over 3. And then we are aware that we have a reaction over here, which is AY. And then the thing now is this. The moment about point A is going in a clockwise direction. Okay. Now, I think everything is fine for all of you until moment at point A is going in a clockwise direction. Why is it not going in the anti-clockwise direction? Is the question to be asked. Okay. And why is it clockwise? Because, okay, anyone can you remember why is it clockwise? Anyone? Can anyone remember? It's okay. Okay, I can't remember. So then when I was doing, I was reading text, I said, oh, that's why. Okay, so it's in that direction. So moment about A is clockwise because okay, of positive shear and positive bending moment assumption. Okay, so what do I mean by that? Okay, so positive shear and positive moment annotation goes like this. And if I start drawing this, you will remember. If our structure, okay, so our structure, if we look at our structure, right, and we want to know what is the shear force and bending moment at point alpha, okay, so positive shear is coming down, V alpha, and positive bending moment is going in the anti-clockwise direction, okay, right? And then if we were to carry out now alpha now is on the left hand side now, right? So when that's the case, positive shear assumption, V alpha, and positive bending moment, M alpha is in that direction. So when this is the case, if you were to see this configuration, and over here, when we have this configuration over here, is because we are assuming positive shear and positive bending moment assumption. Are we clear? This is very important because if not, it can go either way. And if you flip the direction wrongly, the answer will be wrong. Are we clear? Okay. So if that's the case, I'm going to stop here. Have a fantastic weekend and don't be too stressed. I'll see you guys next week. Bye.